So when it comes to now a differential surface vector, like I said, the unit vector of this normal to this wall surface taken out of the spherical surface that we have here is going to be the unit vector along the direction of the vector. And that is just now going to be equals to r d theta then times r sin theta in 5, which is here. So meaning r by r, that will give an r squared sin theta, the theta, then the phi, and then this is going to be in the what? Direction of the radius, r direction, as we can see. So you can see now, we've now have express both vectors. We have the electric fluxes here, that of the differential surface vector. But we do replacement if we're to do that, since both the electric flux density and that of the differential surface are in the same direction. You can see that in that case, their units, right? The unit vectors is going to be what? You do the dot product, that is going to give you 1, right? As a result, then you just have what? Right? You just take the surface integral of what? R squared sin theta v phi, and that is going to give you the surface area of a sphere, which will be 4 pi r squared. So he has kept some of the mathematics here, but what we do is that we replace the r and then r squared sin theta. You integrate with respect to what? The theta, and then the phi, that is going to give you what? The surface area of a sphere, which is 4 pi r squared, and then we have this. So now we make the r component of the electric flux density sounded, and that is going to give us this formula, right? Now, bear in mind that when it comes to now electric flux density, we know that it's going to be close to the permeability of free space time electric flux density. Well, we know electric flux density equals to charge over 4 pi r square, right? Then that's where we get our electric flux density. And if we're to compare both of these equations, right? We have equation 1, because now that I've gotten the r component of the electric flux density, we can come and now write as a vector form, and we just add a unit vector, we get this. So if we are comparing these two formula that we have, you can see that everything is the same except the total electric flux of charge. So they become the same. So we equate these two. That means you can see that means the total electric flux is the same as the charge, the enclosed charge, and that is what we refer to as Gauss's law. So this is how we are able to prove Gauss's law. And anytime you are asked to find the total electric flux, or in this case, the electric flux density, we can always use Gauss's law to find this. And we can use this kind of Gauss's law in situations whereby we are dealing with a symmetrical surface. As you can see, a spherical body is symmetrical in the sense that if we were to divide into two, you have two equal halves in that regard. And that's why in the case we have all the other components of the electric flux density, because it's a spherical body, a symmetrical body, and then we're able to get this as a result. And this is what Gauss's law is all about. And this is using Gauss's law to find the electric flux density of a point charge enclosed by a surface. And the final formula here becomes charge over 4 pi r squared. That's what you get here. See you in the next video. Bye-bye.